Imagine living in a vast city, but when you step outside, instead of bustling urban districts, all you see is an endless empty expanse. What sounds like a scene from a science fiction movie is, in fact, the true picture of our own Milky Way's place in the universe. The universe, with its hundreds of billions of galaxies and enormous cosmic structures, is often described as a cosmic web, a vast network where matter is arranged in glowing filaments connecting galaxy clusters. But what has surprised scientists is this. Our galaxy, the Milky Way, does not sit in the middle of a dense node of the web, but rather inside a giant cosmic void stretching more than 1 billion light-years across. This emptiness has been named the KBC void, after 3 researchers, Keenan, Barger, and Cowie. The idea of the KBC void isn't new. Astronomers have speculated about it for decades. Only in recent years, with advanced observations and massive telescope datasets, have scientists begun to confirm that it is very likely we truly live in a cosmic underdensity, where matter is about 20% less dense than the universal average. This is more than just a fascinating discovery. It strikes at the heart of fundamental cosmological assumptions. Could it be that the Copernican principle, the idea that we are not in a special place, but in an ordinary, homogeneous universe, is being challenged? If the cosmos is not uniform even at billion light-year scales, then our measurements of key quantities, such as the universe's expansion rate, the Hubble constant, or even the very nature of dark energy, might be skewed. When a scientific finding shakes both philosophy and methodology, it deserves deep reflection. In this long-form exploration, we will dive into the origin and nature of the KBC void, how it was discovered, its scale, and why astronomers care about it. The scientific impact, what living inside a giant void means for cosmological models, the heated debate over the Hubble tension, and our understanding of dark energy and dark matter. The philosophical perspective. Does the Milky Way's position inside a void undermine the principle that we are not in a special place in the universe? The human meaning. How might our self-image change when we realize we are drifting in a quiet emptiness, rather than surrounded by cosmic hustle and bustle? Ultimately, this article is not just about cold scientific facts. It is an invitation to reflect on humanity's place in the grand cosmic picture. Sometimes, a discovery that seems distant and abstract can fundamentally reshape how we define ourselves. The large-scale structure of the universe, the cosmic web. When we look up at the night sky, we see only tiny points of light, stars, planets, and the Milky Way. But this is just a tiny slice of reality. With modern telescopes, humanity has uncovered a breathtaking view. The universe is not a random sea of galaxies, but a vast network structure known as the cosmic web. The cosmic web consists of enormous structures stretching hundreds of millions to billions of light-years. Within it, filaments, dense threads of galaxies, galaxy clusters, and dark matter. These are the highways along which matter flows into larger structures. Clusters, giant concentrations containing thousands of galaxies. For example, the Virgo cluster near the Milky Way. Voids of vast, empty regions with extremely low matter density, where galaxies are scarce. To picture it, imagine a sponge. The fibrous strands form a connected network, while the holes are empty gaps. The universe's galaxies and dark matter follow a similar pattern. This realization didn't come overnight. In the 1970s and 1980s, large-scale galaxy surveys revealed that galaxies are not randomly distributed. A groundbreaking map, the CFA Redshift Survey, first showed the presence of enormous galaxy walls and giant voids. Later projects such as the Sloan Digital Sky Survey (SDSS) and the 2DF Galaxy Redshift Survey painted an even clearer picture. The universe is structured like a cosmic foam. Voids, the cosmic deserts. If galaxy clusters are crowded cities, then voids are the lonely deserts of the cosmos. A single void can span tens to hundreds of millions of light-years across. Some even stretch over 1 billion light-years. Inside a void, the density of galaxies and matter is only 10 to 20% of the cosmic average. This means that if you were living inside a void, the distant night sky would look far emptier, with far fewer galaxies to observe. Yet voids are not completely empty. A few galaxies still exist within them, often small, faint, and isolated. Astronomers call these void galaxies, and they have unique properties. For instance, They form stars less actively and interact less with neighboring galaxies. Voids are crucial in cosmology because they make up over 80% of the universe's total volume. In other words, most of the universe is empty space, while the structures we usually talk about, galaxy clusters and filaments, occupy only a small fraction. The Copernican principle and the hypothesis of homogeneity. For centuries, humanity tended to believe it was at the center of existence. But since Nicholas Copernicus proposed the heliocentric model, and with later confirmations from Galileo, Kepler, and Newton, we have gradually accepted that Earth is not special. It is just one ordinary planet orbiting the Sun, which itself resides in a fairly typical galaxy within a vast universe. This idea is known as the Copernican principle. In cosmology, it extends into the cosmological principle, which states, the universe is homogeneous on sufficiently large scales. The universe is isotropic, it looks the same in every direction. These principles form the foundation of modern cosmology, especially the lambda-CDM model, lambda cold dark matter, the standard framework that explains cosmic expansion, dark matter, and dark energy. However, if the Milky Way truly lies inside a giant void like the KBC void, then the assumption of large-scale homogeneity is called into question. This raises several profound questions. Are we actually special by living inside a rare cosmic underdensity? Could fundamental cosmological measurements, such as the universe's expansion rate, be biased by the effects of the void? A brief history of cosmic void research. The existence of cosmic voids was not recognized in early astronomy. For hundreds of years, astronomers focused on cataloging stars, nebulae, and later galaxies. Only with the development of redshift surveys could humanity map the three-dimensional structure of the universe. 1970s, the birth of large-scale galaxy surveys. The first galaxy maps showed that galaxies are not randomly scattered. A landmark 1978 study by Tift and Gregory, University of Arizona, reported unusual gaps between galaxy clusters. 1980s, a turning point came with the CFA Redshift Survey. In 1981, Davis and colleagues announced the discovery of the Boötes Void, an enormous region 330 million light-years across. Within that vast volume, thousands of galaxies were expected, yet only a few dozen were found. This revelation brought the concept of voids into modern cosmology. 1990s, 2000s, with projects such as the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey, SDSS, the universe's structure emerged in exquisite detail. Tens of thousands of voids were cataloged, classified by size and density. Astronomers realized voids were not rare anomalies, but fundamental building blocks of cosmic structure. After 2010, with increasingly precise data, cosmologists began asking, if we live in a void, how does that affect cosmological measurements? In 2013, Ryan Keenan, Amy Barger, and Lennox Cowie proposed what is now called the KBC void, a vast underdense region roughly 1 billion light-years in diameter, possibly containing the Milky Way itself. This was not just a geometric observation, it tied directly into debates such as the Hubble tension. The role of voids in modern cosmology. Today, voids are no longer dismissed as empty gaps, but are recognized as essential tools for science. Some of their key roles include 1. Natural laboratories for cosmology. With their extremely low matter density, voids act as cosmic vacuums, where the effects of dark energy and cosmic expansion are more pronounced. Studying their growth and shapes allows scientists to test different cosmological models. 2. A key to the Hubble tension. One of the biggest current debates is the discrepancy between two methods of measuring the Hubble constant h. Local measurements, Cepheid variables, and type Ia supernovae yield a higher value. Early universe measurements, cosmic microwave background, or CMB, give a lower value. The gap between them is too large to be explained by statistical error alone. One hypothesis is that if we live inside a void, the local expansion rate would appear higher than the cosmic average, creating the illusion of a mismatch in h. 3. Testing dark matter and dark energy. Voids respond sensitively to dark energy. If dark energy truly dominates, voids expand faster than they would in a matter-only universe. Measuring their evolution is therefore a direct probe into the nature of dark energy. 4. Unique environments for galaxies. Galaxies inside voids often show striking differences. Fewer interactions, fewer collisions, and slower star formation. This makes voids valuable laboratories for comparing galaxy evolution in cosmic deserts versus cosmic cities, clusters. From once being obscure, voids are now central to cosmology. They dominate the universe's volume and hold keys to unraveling its biggest mysteries. Dark energy, dark matter, and especially the Hubble tension. If the Milky Way truly resides within the KBC void, it may not be a mere coincidence. Instead, it could force us to rewrite part of modern cosmology. Part 2. What is the KBC void? Definition and name. The KBC void is named after 3 astronomers, Ryan Keenan, Amy Barger, and Lennox Cowie, who published a landmark 2013 study on galaxy distribution in our cosmic neighborhood. They proposed that the Milky Way and its neighbors are not located in a typical region of the universe, but instead sit inside a colossal void over 1 billion light-years across. Other voids had been discovered before, such as the Boötes void, 330 million light-years across. But the KBC void stands out for 2 reasons. It is vastly larger than previously known voids. Most strikingly, we are inside it. If the universe is like a sponge, other voids resemble small pores scattered throughout. The KBC void, by contrast, is more like a gigantic cavity within which our entire galaxy drifts. This runs counter to scientific intuition. The Copernican principle tells us we should not be special, so the chance of happening to sit inside such a rare void should be very low. Yet, mounting evidence suggests this may indeed be reality. Scale and density of the KBC void. Immense size. Estimates suggest the KBC void has a diameter of about 1 to 2 billion light-years, making it 3 to 6 times larger than the Boötes void, and among the largest cosmic voids ever identified. To put this into perspective, light traveling at 300,000 kilometers per second would take over 1 billion years to cross from one edge to the other. Even a spaceship moving close to light speed would need billions of years to traverse it. Lower than average density. Inside the KBC void, the density of matter, including galaxies and dark matter, is about 20% lower than the cosmic average. This means fewer galaxies exist here. Galaxies are spaced farther apart. Some regions are almost entirely empty. Boundaries. Like other voids, the KBC void does not have sharp edges. Instead, it gradually transitions into denser regions of filaments and clusters. At the boundaries, galaxies gather more densely, forming cosmic walls. Discovery process and observational evidence. Initial survey. In 2013, Keenan, Barger, and Cowie analyzed data from several galaxy surveys. They compared the density of bright galaxies near the Milky Way with that of more distant regions. The results showed that galaxies within a radius of several hundred million light-years were significantly sparser than expected. Confirmation by later studies. In the 2020s, large surveys such as Pan-STARRS 1 and the Dark Energy Survey (DES), along with analyses of supernova data, provided independent support. Research teams in Japan, the US, and Europe reported that observations of the local expansion rate of the universe are consistent with the KBC void hypothesis. Some studies even suggest that this local underdensity may be the most plausible explanation for why local measurements of the Hubble constant give higher values than those derived from the cosmic microwave background, CMB. Debate. Not all scientists agree. Some argue the KBC void may simply result from observational bias or random clustering in galaxy distributions. Still, more and more data appear to support the hypothesis. Why is the KBC void so special compared to other voids? Tens of thousands of voids of different sizes have been cataloged. So why has the KBC void drawn so much attention? There are 3 main reasons. 1. Its gigantic scale. Most voids range from 30 to 300 million light-years across. The Boötes void, long considered massive, measures 330 million light-years. By contrast, the KBC void spans over 1 billion light-years, making it 3 to 4 times larger. This scale makes it a statistical outlier. According to the lambda-CDM cosmological model, the probability of such a large void existing is extremely low. That raises the question: is our current model missing something fundamental? 2. Its location. We are inside it. Most voids are far away, observed from the outside. The KBC void is unique because the Milky Way lies inside it. This means our local observations may be biased by this environment. Measurements of cosmic expansion, matter density, and other parameters could be systematically skewed if we don't account for the KBC void. In other words, our special position might directly affect nearly every cosmological measurement we make. 3. Its direct link to the Hubble tension. The ongoing disagreement over the Hubble constant h is one of cosmology's hottest debates. The discrepancy is large enough that it might require new physics to resolve. The KBC void is seen as a strong candidate explanation. If we are inside an underdense region, the local expansion rate would be higher, making local measurements of h larger, while the CMB gives a lower global value. This matches the observed discrepancy. Scientific debate within the community. While the KBC void hypothesis is compelling, it has sparked significant debate. Current views fall into three main camps. Strong supporters. Some scientists argue that mounting evidence favors the KBC void. Data from type Ia supernovae and nearby galaxy maps consistently show a matter density deficit around us. They believe this could be the missing piece that explains the Hubble tension without invoking new physics. Skeptics and critics. Others counter that the KBC void size and depth may be overestimated. Galaxy surveys could suffer from selection bias, making the region appear emptier than it really is. Even if the void exists, the discrepancy it explains is too small to fully resolve the Hubble tension. For them, voids are part of the story, but not the full solution. Neutral/intermediate views. Many researchers take a middle ground. Voids must be considered, but they alone cannot solve the problem. They propose combining the effects of voids with possible new physics, e.g., dynamic dark energy or massive neutrinos, for a more complete explanation. In summary, the KBC void is a cosmic underdensity of colossal scale, about 1 billion light-years across, with matter density 20% below average. What makes it truly remarkable is not just its size, but the fact that we are inside it. If real, the KBC void may be key to resolving one of modern cosmology's biggest puzzles, the Hubble tension. Yet the debate continues, and consensus has not been reached. One thing is certain: the KBC void forces astronomers to rethink the Copernican principle, reminding us that humanity's place in the universe may not be as ordinary as we once believed. Part 3: Scientific implications. The Hubble tension, the biggest crisis in modern cosmology. One of the main reasons the KBC void is so important is its connection to the Hubble tension, the mismatch between different measurements of the Hubble constant h. What is the Hubble constant? The Hubble constant, denoted h, describes the current expansion rate of the universe. It tells us how fast space expands per unit distance. For example, if h equals 70 kilometers per second per mpc, then a galaxy 1 megaparsec, 3.26 million light-years, away would recede at 70 kilometers per second due to cosmic expansion. H is critical because it directly determines the age of the universe, higher h younger universe, the observable size of the universe, the validity of cosmological models and fundamental physics. 2 methods, 2 results. Currently, 2 main methods give conflicting values. Local measurements, based on distances to Cepheid stars and type Ia supernovae. Result: h is almost equal to 73 to 74 km/s/mpc. Early universe measurements, based on cosmic microwave background (CMB) data, particularly from the Planck satellite. Result: h is almost equal to 67 to 68 km/s/mpc. The 9% discrepancy is far beyond statistical error, creating the so-called Hubble tension, a problem many scientists consider a crisis in cosmology. How could the KBC void explain this? If the Milky Way resides inside a giant void, then local matter density is lower than average. Space here expands faster than in denser regions. As a result, measurements using local sources within the void yield higher values of h. Measurements from the CMB, the universe as a whole, give lower values. In other words, the KBC void could naturally produce the very discrepancy we observe. Limitations of the KBC void hypothesis. While attractive, detailed analyses show that the KBC void size and depth are not sufficient to explain the entire Hubble tension. A void of this scale could account for a difference of about 2 to 3 km/s/MPC, whereas the actual gap is 5 to 6 km/s/MPC. This means the KBC void could be part of the solution. But to fully resolve the tension, we may still need new physics, such as dynamic dark energy, massive neutrinos, or modifications to the lambda CDM model. Dark matter and dark energy in the context of the KBC void. Dark matter and its role in voids. Dark matter makes up about 27% of the universe's total energy content. Though invisible, it dominates the formation and structure of the cosmos. Inside voids, the density of dark matter is also lower than average. This makes voids ideal laboratories for testing the properties of dark matter. For example, whether it is truly cold, CDM, cold dark matter, or whether it might have additional interactions that standard models overlook. Dark energy and the expansion of voids. Dark energy accounts for about 68% of the universe's energy budget and is believed to be the driver of cosmic acceleration. In underdense regions like voids, its effect is especially pronounced. By measuring the expansion rate of voids and comparing it to theoretical predictions, astronomers can test whether dark energy is simply the cosmological constant, lambda, or whether it has a more complex, dynamic nature. The KBC void and the lambda CDM model. The lambda CDM standard model of cosmology. The lambda CDM model is the dominant framework for understanding the universe's evolution. It rests on three key components. Lambda, the cosmological constant, representing dark energy. CDM, cold dark matter, non-relativistic dark matter that drives structure formation. Baryons, ordinary matter, the stuff of stars, planets, and living beings. Lambda CDM successfully explains the cosmic microwave background, CMB, large-scale structure, and the accelerated expansion of the universe. However, the Hubble tension represents a serious crack in its foundations. How the KBC void challenges homogeneity. Lambda CDM relies on the cosmological principle that the universe is homogeneous and isotropic at sufficiently large scales. But if a void over 1 billion light-years in diameter truly surrounds the Milky Way, that implies the universe is less homogeneous at large scales than previously assumed. Observations within our local universe may not reflect the cosmos as a whole. This forces us to reconsider, is lambda CDM incomplete, or must we relax the assumption of large-scale homogeneity? A hybrid solution. Some researchers suggest we should not treat the KBC void as a falsification of lambda CDM, but rather as a local correction. The standard model remains valid globally, but at the local scale we need to account for environmental effects like massive voids. In this view, the KBC void is a perturbation to include, not a reason to discard the entire framework. Impacts on other cosmological measurements. Beyond the Hubble constant, the KBC void could affect several other key observations. Cosmic distance measurements. Light from distant sources passing through a void is affected by gravitational potential differences. This alters the luminosity-distance relation. If unaccounted for, distance estimates, e.g., from type Ia supernovae, may be biased. Weak gravitational lensing. Weak lensing, tiny distortions in galaxy shapes due to matter distribution, is crucial for mapping dark matter. A locally underdense region could contaminate statistical analyses of lensing signals. Peculiar velocities. Galaxies move not only with cosmic expansion but also due to local gravitational pulls. Living inside a void alters the peculiar velocity field of nearby galaxies, which must be corrected for when extracting cosmological parameters. Age of the universe estimates. If the local expansion rate is higher than average, nearby observations imply a younger universe, while CMB-based estimates suggest an older one. This mismatch is a root of the Hubble tension itself. Thus, the KBC void affects not just H, but also many of the yardsticks of modern cosmology. It directly challenges the assumption of large-scale uniformity that underpins lambda CDM. Still, rather than overthrowing the standard model, many scientists see the KBC void as a local perturbation that must be included. This preserves lambda CDM while opening a new frontier, studying the role of large-scale inhomogeneities in cosmology. Alternative models and future scenarios. LTB universe, Lemaitre, Tolman-Bondi models. One alternative often discussed in connection with giant voids is the LTB model, a universe that is not homogeneous, where we might live near the center of a vast cosmic bubble. If true, part of the observed acceleration could come not from dark energy, but from the geometry of the void itself. This idea was once a serious candidate to explain the 1998 discovery of accelerated expansion, but later evidence showed that dark energy is still required. Nevertheless, the KBC void reminds us not to dismiss void-based cosmology entirely. Instead, it could serve as a supplementary ingredient to lambda CDM. Dynamic dark energy. If voids alone cannot explain the Hubble tension, another possibility is that dark energy is not constant, but varies over time or space. In voids, dark energy's influence might be amplified compared to denser regions. Observing huge voids like the KBC could provide critical data to test whether dark energy is truly constant or dynamic in nature. Modified gravity. Another direction is to assume that Einstein's general relativity is not entirely correct on cosmological scales. Some theories such as F are gravity extended mond, or scalar tensor theories have been proposed. Voids are ideal environments for testing these ideas because gravity there is weaker, so any deviations from Einstein's predictions would be easier to detect. Future scenarios. In the next 10 to 20 years, next-generation telescopes such as the Vera Rubin Observatory, Euclid, and the Roman Space Telescope will provide detailed 3D maps of cosmic structure. If the KBC void is firmly confirmed, it would be direct evidence that cosmology needs adjustments. If, on the contrary, new data show the void is much smaller, attention may return to dynamic dark energy or other new physics scenarios. From this analysis, a few key points can be drawn. KBC void and the Hubble tension. A giant void around the Milky Way could explain part of the discrepancy between H measurements. However, it is not large or empty enough to fully resolve the problem. Impact on the lambda CDM model. The principle of homogeneity is challenged, at least on the billion light-year scale. Lambda CDM may still be valid, but needs corrections to account for large-scale inhomogeneities. Consequences for other cosmological probes. Distance measurements, weak lensing, and peculiar velocities are all affected. If the KBC void is ignored, these results could be biased. Alternative models, LTB cosmologies, dynamic dark energy, or modified gravity may all be relevant. Voids serve as a natural laboratory to test these scenarios. In short, the KBC void is not only an intriguing astronomical finding, but also a crucial piece in the puzzle of modern cosmology. It reminds us that the universe is far from simple, and even its most fundamental principles must sometimes be placed under the microscope of science. Philosophical perspectives. The Copernican principle and non-specialness. Since Copernicus, modern science has been guided by a fundamental principle. We are not special. Earth is not the center of the universe. The Sun is just one among hundreds of billions of stars. The Milky Way is only one galaxy among billions of others. This principle, known as the Copernican principle, became the compass of cosmology. It asserts that on large scales the universe must be homogeneous and isotropic, with no privileged position. But the KBC void hypothesis forces us to pause and ask, could Earth and the Milky Way really be in a special location within cosmic structure? If we live inside a giant void, do our measurements of expansion rate, matter density, and so on actually represent the whole universe? If the answer is no, then the Copernican principle, the very philosophical foundation of cosmology, has at least been challenged. Humility before the cosmos. There is an interesting paradox. If we live inside a void, then our position is indeed special. Yet this very specialness reminds us of humility, because this specialness does not mean humanity or Earth is important. It is simply a random consequence of cosmic structure formation. We are special in the sense of not being important at all. This is much like being accidentally born at a time when the universe is accelerating in its expansion, a unique moment in an otherwise endless cosmic timeline. Philosophical meaning of randomness. If the KBC void exists, it highlights the element of randomness in our existence. Why did humanity arise in a region of low matter density? Could it be that precisely this low density allowed life to evolve? Since the environment was less disturbed by gamma-ray bursts, supernova explosions, and other cosmic hazards? Some philosophers of science suggest that voids may tie into the anthropic principle. The universe has properties compatible with life, and we observe them precisely because, if it were otherwise, no one would be here to observe at all. The incompleteness of human knowledge. The debate over the KBC void also shows how immature our knowledge still is. We have observed only a small fraction of the visible universe. Even its main ingredients, dark matter and dark energy, are little more than names, with their true nature still unknown. In this context, debating whether or not we live in a void is like standing on the shore, watching a few waves, and trying to draw a map of the entire ocean. Philosophy reminds us, every scientific discovery is not a full stop, but a comma, opening the way to greater questions. Infinity and metaphysical questions. If voids can exist on the scale of billions of light years, then could there be infinitely many voids in the universe? Does the universe have a fractal structure, self-similar at all scales, or does it eventually flatten out? These are no longer purely physical questions but touch upon metaphysics. If the universe is truly fractal, then the concept of overall homogeneity becomes meaningless. In that case, cosmic order lies not in uniformity, but in inhomogeneity itself. This changes the way we think about existence. The universe is not a smooth fabric, but an endless network of dense and empty regions, where life can sprout at random. Life lessons from the KBC void. On the limits of perception. The discovery of the KBC void teaches us that what we observe is never the whole truth. We once believed Earth was the center of the universe. Then we thought the Milky Way was everything. Then we assumed the universe must be homogeneous on large scales. At every step, science has forced us to revise our worldview. If the void truly exists, it is just another step in the unending journey of expanding human understanding. This also applies to personal life. We often believe that what we see and experience is the whole truth. In reality, it is only a small slice of reality. The lesson: always remain open, humble, and willing to change perspective. On existence within emptiness. If humanity truly lives inside a great cosmic void, it is a beautiful metaphor. Even in emptiness, life can flourish and intelligence can grow. This shows that meaning can still be created even in situations that seem empty or devoid of purpose. On a personal level, each of us sometimes passes through our own voids. Moments of emptiness, existential crisis. And just like the universe, it is often from that emptiness that new creativity, vitality, and strength emerge. On the relationship between chance and necessity. If we truly happen to live by chance inside the KBC void, that itself is evidence of the universe's chaos and unpredictability. Yet within this randomness lies a form of necessity. Life finds a way to exist and to rise, regardless of its environment. Eastern philosophy once said, "Being and non-being give rise to each other." The giant void around us reflects this idea. In the absence of dense matter, conditions favorable for life may emerge. On faith and patience. The KBC void is not easy to prove. Scientists have spent decades gathering data to support or challenge its existence. This teaches us an important lesson. Truth takes time. Not everything can be clarified instantly. In life, we often grow impatient, wanting quick answers and immediate clarity. Yet the universe reminds us that even the most fundamental questions, where are we? Is the universe truly homogeneous? Can take centuries to resolve. A mirror of humanity. From a philosophical perspective, The KBC void is not just an astronomical phenomenon, but also a mirror reflecting ourselves. It challenges the Copernican principle, reminding us that being special or not special is merely a matter of how we define our place. It teaches humility, showing how small human knowledge still is compared to the vast universe. It sparks reflection on chance and necessity, on how life can still emerge within emptiness. It emphasizes the importance of patience and faith in the search for truth. In short, if Part 3 shows us the scientific impacts, then Part 4 reveals the human meaning. The KBC void not only reshapes the foundations of cosmology, but also compels each of us to reconsider our place and role within the vast cosmic picture. Part 5: Open questions raised by the KBC void. If confirmed, the KBC void would spark a host of new questions in astronomy. Size and density accuracy. Is the void truly over 1 billion light-years across or smaller? Formation mechanism. How could such a vast void have formed within the 13.8 billion-year history of the universe? Cosmological impact. How does it affect the Hubble constant, galaxy distribution, or weak gravitational lensing? Universality. Are there similar voids elsewhere in the cosmos, or is the KBC void unique? Philosophical implications. If the universe is not homogeneous on billion light-year scales, how should cosmological models be redefined? Answering these questions will require far more powerful tools than those we currently possess. Next-generation telescopes. Vera-C. Rubin Observatory LSST. Expected to begin operations in 2025. LSST will capture images of the entire southern sky every few days. It will produce an unprecedented 3D map of distant galaxies. With this data, we can measure matter density across regions of space and confirm, or reject, the existence of the KBC void. Euclid Space Telescope, ESA. Launched in 2023, Euclid specializes in studying dark energy and large-scale cosmic structures. By observing tens of millions of galaxies, it will allow detailed mapping of voids and comparison with theoretical predictions. Nancy Grace Roman Space Telescope, NASA. Scheduled for launch in 2027. With a field of view 100 times larger than Hubble, Roman will measure cosmic distances with exceptional precision. This will help test the hypothesis that living inside a void biases our measurement of the Hubble constant. Square Kilometre Array SKA, the world's largest radio telescope, spread across South Africa and Australia. SKA will map the distribution of hydrogen throughout the cosmos, providing a skeleton of voids and filaments. The role of artificial intelligence, AI. Modern cosmology generates enormous datasets from LSST, Euclid, SKA, far beyond human capacity to analyze manually. AI and machine learning will be crucial in identifying voids among billions of galaxies. AI can detect subtle patterns that humans might overlook, such as small distortions in galaxy distributions caused by voids. Deep learning will also aid in simulating the universe, generating thousands of scenarios to compare against real data. Thus, studying the KBC void will become a prime example of big data cosmology. Simulations and supercomputing. Observation alone is not enough. We must also simulate the universe to understand how voids form. Projects like Illustris and Millennium Simulation have modeled the universe with billions of particles representing galaxies. In the future, with exascale computing power, we may simulate the universe down to the detail of galaxy groups, testing whether the KBC void is theoretically possible. Simulations also allow us to explore alternative models, dynamic dark energy, modified gravity, and examine how voids might form differently under each scenario. The future of cosmic remote sensing. In the 21st and 22nd centuries, humanity may develop space telescopes positioned far from the Sun, beyond Earth's orbit, reducing interference and increasing sensitivity. A network of telescopes on the Moon, taking advantage of its stable environment, thin atmosphere, and low temperatures. Next-generation gravitational wave interferometers such as LISA, which could probe cosmic voids through their influence on gravitational waves. These technologies will elevate the study of voids to an entirely new level. Applications beyond astronomy. The fascinating part is that studying voids is not only valuable for cosmology but also impacts many other fields. Data science, techniques used to process galaxy surveys can be applied in healthcare, finance, and climate research. Fundamental physics. Confirming voids helps us better understand dark energy, paving the way for a unified theory of physics. Philosophy and education. The KBC void can serve as an inspiring story, reminding humanity of both our smallness and our drive to explore. Challenges ahead. Despite increasingly powerful telescopes, mapping the boundaries of voids remains difficult. Galaxies are unevenly distributed, creating statistical uncertainties. Distances are inferred from redshift, but are distorted by peculiar velocities, which can warp cosmic maps. Dust, gravitational lensing, and other effects complicate measurements further. To confirm the KBC void, scientists must combine multiple methods: optical, infrared, radio, and even gravitational waves. Current cosmological simulations are built on the lambda CDM model. If giant voids exist, we may need to adjust initial conditions or build entirely new models of an inhomogeneous universe. But this is extremely challenging, since it breaks the principle of homogeneity, which underpins modern cosmology. Today, some surveys, like Cosmic Flows 3, support the KBC void, while others find no clear evidence. This may be due to differences in analysis methods, or because the void is not smooth but has complex, irregular boundaries. This means decades of additional data will be needed before we reach a firm conclusion. Studying the universe requires multi-billion-dollar telescopes, national-level supercomputers, and long-term international collaboration. Political competition could also influence progress. Scientists must also weigh priorities. Is investing in void research more worthwhile than searching for extraterrestrial life? Balancing global resources with scientific ambition is not an easy task. Looking ahead, the study of the KBC void and large-scale cosmic structures will likely follow several directions. Observations, LSST, Euclid, Roman, SKA, will provide the most precise 3D maps ever, confirming or disproving the existence of the massive void around the Milky Way. AI and big data, essential tools to process hundreds of petabytes of data, identify voids, and detect cosmic patterns. Simulations and supercomputers, to test hundreds of theoretical models, from modified lambda CDM to dynamic dark energy. Remote sensing technology, telescopes on the moon, in deep space, and even instruments to detect gravitational waves. Broader applications, beyond cosmology, this research will advance data science, fundamental physics, and even human philosophy. The road ahead will not be easy. Observational challenges, theoretical limits, conflicting data, and resource constraints remain. Yet, these very obstacles are what drive creativity and global collaboration. In other words, the KBC void is not just an empty space in the universe, but also a promise for the future of science, that humanity will continue to push forward beyond the limits of understanding in search of answers to the greatest cosmic questions. Part 6. The void is not nothingness. Throughout this journey, we have moved from the concept of voids to evidence for the KBC void, and then to its scientific, philosophical, and technological implications. One truth becomes clear. A void is not nothingness, but a living part of the universe's structure. If the KBC void exists, it is not just a scientific curiosity. Challenges the Copernican principle and the lambda CDM model, the very foundations of modern cosmology. Offers a potential solution to the Hubble tension, one of the hottest debates in physics today. Opens opportunities to study the nature of dark energy and dark matter. And above all, raises a philosophical question. Are we truly in a mediocre position, or do we occupy a special space in the cosmos? Studying voids cannot be done by a single nation or laboratory. It requires space telescopes costing billions of dollars, networks of supercomputers capable of simulating the universe, open, shared data so that thousands of scientists worldwide can collaborate. The universe has no borders, and cosmic science should be no different. The KBC void may stand as proof that only through collaboration can humanity truly understand the vast cosmos. At a deeper level, the story of the KBC void reminds us the universe is not always crowded or lively. There are immense silences, vast cosmic solitudes. The Milky Way, along with Earth, drifts within one such silence. But this is not cause for despair. On the contrary, it gives us a greater responsibility to create meaning for ourselves through discovery, creativity, and connection. If the universe is a great symphony, then voids are the pauses that make the music resonate. Call to action. Loudspeaker at this point, I want to leave you with a call. Support space science. Follow projects like LSST, Euclid, SKA, Roman. Stay informed, share knowledge, and advocate for continued investment in fundamental science. Join the knowledge community. If you're a student, seek opportunities to join research groups or open projects. If you're a science enthusiast, spread scientific thinking within your community. Reflect on humanity's place. Knowing that we live inside a cosmic void does not diminish human value. On the contrary, it highlights our uniqueness. Let this humility inspire us to build a more connected world, cherishing the rare gift of life on Earth. The KBC void may be confirmed or one day disproven, but the journey itself already expands our understanding. The universe is an unfinished story, and we are its storytellers. Perhaps one day, when future generations look back, they will say, "It was from the questions about cosmic voids that humanity learned to overcome the voids within ourselves and move closer to the truth." Milky Way, so let us support science, for in exploring the universe, we are ultimately exploring ourselves.